Hello and welcome back to the Ways of Math. I'm your host, Dan the Math Man. And today we're going to continue our series on Introduction to Sets. So this is part 4 of this multi-part series. So today in this video, we're going to discuss the set operations, including the union of sets, the intersection of sets, set difference, also known as set subtraction, and the complement of a set. Okay? These are all critical concepts, and this is how we perform operations on sets. This is just some of the operations, but these are the big ones that we definitely want to know going forward. Okay, let's jump right in. Okay, so we begin with a definition, just like we have been previously. So our definition. Okay, so this is going to be the definition of union. Okay, so the union, and since this is the term we are defining, we're going to underline that. That's important. So the union of two sets, and we'll call these sets A and B, okay, is the set that contains all the elements from A and B. Okay, so this is all the elements that are contained in A and B. We essentially just kind of throw them all together into one set, and that gives us what's called the union of the sets. Okay, and this is denoted A with this little U. Okay, be careful not to make this look like the letter U, okay, like we would for a universal set, but this kind of cup shape, that's kind of what's more important, is it looks like a cup. A union B, and this is read as A union B, okay? More formally, okay, so this is how we would formally write this. The set A union B is the set defined by element X, such that X is an element of A, or X is an element of B. Okay? So A union B is the set of all elements that are either in X, or that's the set of all elements either in A, or they're in B. Okay? They could be in both, so this or is not exclusive. It just means that every element that we have in A, we're going to put in there, and every element in B, we're going to put in there. So it doesn't matter whether it's an A or B, it's going to be added into this set, this union set. Okay? So let's take a look at some examples of this. Okay? I'm going to get started here. All right, so let's say we define a set A as being the set 1, 2, 3, 4. And let's say we define the set B as the set 2, 4, 6, 9. Okay? Then the set A union B is a set that includes all the elements from either A or B. Okay? So we need to have 1, that's an A. We need to have 2, that's in both sets, so we just pull out the 2. We need to have 3, because that's at least an A there. Okay. We need 4, it's in both sets, but we just need one of the 4s brought down. Okay. We need 6, even though it's not an A, 6 is in B, so we do need that in there. And lastly, we need 9, because 9 is in B. Okay, so A union B is this set 1, 2, 3, 4, 6, 9. Okay. Let's do another example. Alrighty, let's say we define A as being the set 1, 3, 5, 7. Let's say we define the set B as being the set 2, 4, 6, 8. Okay, two completely different sets, that's okay. A union B is going to be the set that brings all these elements together. So we need a 1 from A, we need the 2 from B, we need the 3 from A, the 4 from B, 5 from A, 6 from B, 7 from A, and finally 8 from B. Okay, so when these sets are disjoint, when they're completely different, they have no common elements, then the union of the two sets is just all the elements thrown into one set. But when we have duplicates, notice we only write the duplicates down once. We don't write them multiple times because that's irrelevant to add the extra set. Okay, let's do one final example. So let's say we define A as the set 0, 2, 4, 6, ... right? Remember, these are called ellipses, so this means to continue on building this set in the same fashion. So we have 0, 2, 4, 6. So we're going to continue building with even integers there. Okay, and so that's an unending set. It's an infinite set. And set B, the set 1, 3, 5, with the ellipses, this ... Okay, so this is going to be inferred as all the odd numbers. So 1, 3, 5, 7, 9, etc. So this is another infinite set. Okay, if I bring these together, notice what I'm going to get. So A union B is all these even integers, including 0, all these odd integers. So I'm going to end up with 0, 1, 2, 3, etc. And this is one of our commonly known sets that we described last time. This is the set N of natural numbers. Okay, and that's how union works. Pretty nice. All right, so let's discuss our next operation. Okay, so we need another definition here. Definition. This time we're going to define set intersection. Okay, so the intersection, okay, again, this is what we're defining. I'm going to underline this, keep this in mind. This is set intersection, okay, of two sets. Call them A and B. So the intersection of two sets, A and B, is the set that contains all elements that are, in common. Okay, namely in both sets. A and B. Okay, so all the elements that are in common to both A and B. So what are elements that are in both of the sets? Okay, and this is denoted A intersect B. Kind of looks like a little upside down union symbol, right? The union symbol was that cup symbol. This is now a cap, like a little cap symbol. Okay, and this is read A intersect or intersected, okay, with B, or A intersect B. Okay, so this is the symbol for that. And then more formally written, this is the formal way to write it. A intersect B is the set of elements, call them X, such that X is an element of A and, that's the difference here with the union, this is and, means it must satisfy both. X is an element of B. So it's an element of A and it's also an element of B. So this element, in order to be contained in this intersection, must be both in A and must be in B. Okay? Let's do a couple examples of that. Alrighty. So let's say we define our sets A as being a set 1, 2, 3, 4, kind of a simple set, and let B be the set 2, 4, 6, 9. Okay? And so what we're looking for when we have this intersection of A and B, we're looking for the elements that are in both A and B. And we see here 2 is in both sets. And we also see that 4 is in both sets. Notice nothing else is in both sets, right? 1 is not in B, and 3 is not in B. So therefore, there are no more shared elements. There's no more common elements. Okay? So then the intersection A and B will be precisely these two elements, 2, 4, and that's our intersection. Okay? Let's do another example. Suppose we let our set A be, gotta be careful with these curly brackets, little braces, 1, 3, 5, 7. Let's say we define B to be the set 2, 4, 6, 8. Okay? Then A intersect B is equal to, so notice there's nothing in common, right? 1 is in A, but it's not in B. 3 is in A, not in B. 5 is in A, not in B. 7 is A, not in B. Okay? So this is actually an empty set. So remember how we denote that? We can denote it by 2 braces without any elements inside, right? Or we could write that with our special notation for empty set, okay, which is the circle with a slash through it. Okay? And that denotes the empty set. Okay? So that's how intersection works. All right, so let's move on to our next set operation. And this is going to be called set subtraction or set difference. You might also hear the word set difference. I like the word, for this context, I like to use the word set subtraction. I think it kind of rings a note a little bit better, especially in elementary contexts, to think of it as subtraction, because that's essentially, you'll see from the definition why I think subtraction makes a little more sense, okay, because we're subtracting elements or removing elements from a set, okay? All right, so with the definition, the subtraction or difference, oops, if I can spell today, subtraction, and again, that's what we're defining, set subtraction, of a set B from a set A, right? So we're subtracting B from A, okay? Is the set of elements in A that are not in B. Okay? So this is the set of elements in A, but we take out any elements that might also be in common with B. Okay? So now if A is completely different from B, then the subtraction does nothing. But if we have elements in common, then whatever is in A and also in B, we remove those elements of B from A. Okay? So this is denoted as A with this backslash B. Okay? Or sometimes you might even see it as A with a minus sign B. Okay? And this is read, we read this as either the set A subtract B, okay? Or sometimes you might hear it read as A minus B. But be careful when using minus because we need to make sure we are understanding context, that we're dealing with sets and not values like integers or numbers or variables. Okay, because minus, of course, has a different meaning in that case, and even with subtraction, it does as well. So we want to make sure we're talking about sets before we say a set A minus the set B. So a lot of times it's preferred to say A subtract B, so subtract the set B. Okay, now this is formally written. So A subtract B is written as a set of elements x, okay, such that x is an element of A and x is not an element of B. So again, this element symbol with a slash through it means it's not an element of. So this is the elements that are in A and they're not in B. So if they're in B, we can't have them in this set. Even if they are in A, we want to remove the elements from B. Okay? So a real simple example for that one. Suppose I have a set A, 1, 2, 3, and a set B that's 1, 4, 9. Okay, the set A subtract B. So what I'm going to do is I want to take all the elements in A, but if it's in B, I'm going to remove it from this set. Okay, so you start with A, remove elements of B from it. Okay, so I start with 1. 1 is in B, so I remove that element. So I don't put a 1 in this set. I then move to 2. 2 is not in B, so it's not going to be subtracted. So I include 2 in that set. I then move to 3. 3, again, is not in B, so I can keep 3 in the set. And that's it. I don't consider the remaining elements of B because I'm only subtracting B from A. So I start with A and only remove the elements that are in common with A and B. Now I can think of kind of the other direction of this case. So B subtract A. So this time I start with the set B and I remove the elements that are in common with A. So I want all the elements in B, but remove the elements that it shares with A. Okay, so I go to my set B. I start with 1. 1 is in common. 1 is in A, so I don't write 1. 4 is not in A, so I would write the 4. 9 is not in A, so I write the 9. And then I stop. Again, I don't consider the remaining elements in set A. I want to only remove the ones that it shares in common. And so that would be my set B subtract A. Okay. Now the next operation, this is going to be the last operation we talk about today. A very important operation, okay? And it's the set complement, so the complement of a set. Okay, our last definition for today. All right. So the complement, and again, this is what we're defining, so I will underline that. We're defining the set complement, okay, of a set A is the set of elements in the universal set. Remember the universal set U, universal set, number capital U, okay, not including elements of A. Okay, so what we're going to do when we want the complement of A is we need to have this universal set U defined, because we're going to take the entire set of elements in U and then remove the elements of A from U, and that's defined as being the complement. Okay, now how is this denoted? It's denoted in multiple ways. We have this A with a little C up there, okay, or you might sometimes see A with a little apostrophe. Okay, both of these they mean the same thing. They're both read as A complement. So this is read as A complement. So it's whatever the set is, the set name, as the A complement. Okay, formally written. So how will we formally think about this? Well, it's based off of the previous definition with set subtraction. So A complement is the set U, the universal set, subtract the elements of A. Okay, so the complement, if we think of the universe as being all the numbers or all the elements or all the objects that we're talking about in a particular context, then the complement of A is everything in that universal set except for the values of A. So it's kind of like the opposite elements, or the every other element except for the elements in A. Okay? All right. So we're going to do one big example. It's going to deal with all of these operations that we've talked about today. Okay. All right. Example. So for all of these examples, we're going to use the same sets. So we're going to define our universal set for this set of examples. 1, 2, 3, ... ellipses. Okay. 9, 10. Okay. So this is a set of all integers from 1 to 10, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. We're going to define the set A as being the set 1, 3, 5, 7, 9. We're going to define a set B, which is the set 2, 4, 5, 8, 9. And we're going to define the last set C that we're going to use for this. And that's going to be defined as the set 2, 4, 8, 10. Okay? So these are going to be the same for all of these examples. Okay? Now what we want to do is compute the following sets. Okay? So we want to compute A union C. Okay? So remember what the union is. So the union is everything that's in A or everything in C. So we want to take all these elements in A, all these elements in C, kind of throw them all into the same set, and we just don't write any duplicates. Okay, so we want to write all the elements that are in either A or C. Okay, so we have 1 from A, we have 2 from C, we have 3 from A, we have 4 from C, we have 5 from A, we have 7 from A, we have 8 from A, or from C, I'm sorry, 8 is from C, we have 9 from A, and finally 10 from C. Okay, so we have our A union C is 1, 2, 3, 4, 5, 7, 8, 9, 10. That's our union of A and C. Okay, all right, let's do another one. We want to compute A intersect B. This is the intersection, so remember that that's all the elements in A and all the elements in B, so elements that are shared by both A and B. So what elements are in both the sets A and B? Okay? So we're going to go through A and see if the elements in B. So 1, well, that's not in B. 3, well, that's not in B. 5, oh, 5 is in B. So 5 is in both A and B. There's my first element that's in common. 7, that's not in B. 9, that one is in B. Okay, so notice the method that I use in order to determine intersection. I simply pick one of the sets. Okay, if they're the same size, it doesn't matter, but I always like to pick the smaller set if there is one. And then I simply go through that smaller set and see if that's shared. Okay, and then I don't have to look at any remaining elements. Once I go through that whole set, I've gone through all the possibilities where there could possibly be shared elements. And so here's, again, both of these are examples of cases where if you can order the numbers or order the elements in the set, it makes it much easier to perform these operations and prevent missing any kind of elements because we can just kind of count through the set, or whether these are organized alphabetically or organized by number or by size or value. It's a lot easier if everything's organized in order to kind of count through or to traverse through these sets in order to determine what's in the sets that we want to look for. Okay, all right. Let's also compute B complement. Okay, so the complementary set in B. So remember, that's everything that's in the universal set if we take B out of it. Okay, so this time when we do complement, we want to traverse through the universal set. And if we see an element in the universal set that's also in B, we don't write it. If it's an element of the universal set that's not in B, we will include it in our set. Okay? So this, I'm going to count from 1 to 10. So those are all the elements in the universal set. If I see a duplicate in B, I remove it. So 1, well, that's not in B, so I'm going to keep that one. 2, that's in B, so I don't write it. 3, that's not in B, so I'm going to keep that one. 4 is in B, so I skip it. 5 is in B, so I skip it. 6, that's not in B, so I'm going to write that one down. 7, not in B, so I'm going to write that down. 8, well, that's in B, so I skip it. 9, well, that's in B, so I skip that. And then finally 10, that one's not in B, so I'm going to write that down. Okay, so this is the complement of the set B. Okay, all right, let's do another example. So this is B subtract A. So I'm going to start with the set B, and I'm going to remove all the elements that it shares with A, if it shares any. So this time you always want to traverse the first set here. So B is what we want to go through, and then compare that to elements in A. So going through B, I start with 2. 2 is not in A, so I keep that one. Right? Remember, I only remove the elements that are shared or in common to both. 4, well, that's not in A, so I'm going to keep 4. 5, that's in A, right? So 5 is in both, so I want to remove that element from this set. Okay, so I don't put 5 down. 8 is my next element in B, that's not in A, so I don't remove it. I leave it in my set. 9 is the last element, that is also an A, so that one I remove. So there's my complete set there. So B subtract A, or B minus A, is the set 2, 4, 8. Okay? Couple more examples here. Okay? This time we want to compute A intersect C. Okay? So again, so it looks like C is a smaller set. So I'm going to count through C and see if it has anything in common with, remember this is intersection, so I want to see what's in common with a set A. 2, well, that's not an A, so I don't write it. 4, that's not an A, so I don't write it. 8, well, that's not an A, so I don't write it. And finally 10, oh, that's not an A. So they have no elements in common. So therefore this is what? This is the empty set. And again, we denote that either with 2 braces without any elements inside, or we denote that by the symbol for the empty set. Okay, one more, and this is kind of a big one, so we'll do this in 2 parts. This time we want to compute B union C, and then take the complement of that. Okay, so kind of order of operations with arithmetic, I'm going to start from the inside of the parentheses, compute the B union C. Once I obtain that set, I want to take the complement of that set. Okay, so working inside parentheses, I want to figure out what is B union C. So inside here, I'm going to put B union C. So that's all the elements in B that are also, and all the elements in C, all thrown together. Okay, so going through B, I need 2. Let's see, 2 is in C. I need 4, it looks like the next one. Okay, 5 would be the next one. 8 would be the next one. 9 would be the next one. And finally 10, and that one's from C. Okay, scoot this over just a little bit. Okay, so B union C is the set 2, 4, 5, 8, 9, 10. Okay, now I want to take the complement of that. So remember, the complement of this set is going to be everything that's in the universal set except for these elements. Okay, so I'm going to traverse through my universal set and remove the elements that I just found. Okay, so 1, that's not in my set, so I'm going to keep that one. 2, I remove because 2 is in my set. 3, that's not in my set, so I keep the 3. 4 would be the next one. That is in my set. I do not write 4. 5, that's also in my set. I don't write it. 6, that one's not in my set, so I'm going to keep it. 7, again, not in this set, so I keep it. 8, that one's in my set, so I don't write it. 9 is in my set, I don't write it. And finally, 10 is in my set, so I don't write it. Okay, so I've gone through all the universal set. I've removed the elements from B union C, and I obtain my complement set. 1, 3, 6, 7. I know this was kind of long. I did a lot of examples, but I really wanted you to have the best chance of understanding these set operations and how to perform them. Okay, so that concludes our video today. Please stay tuned for the next video in the series. Okay, and always please subscribe to the channel. If you have any comments or suggestions, please add them to the suggestion box below. Thank you for watching the video. I hope you enjoyed, and have a wonderful math-filled day.